we're going to look at the definite integral now. All right. So it says use the formula for the area of a circle to evaluate the integral from 3 to 6 of the square root of 9 minus x minus 3 quantity squared dx. So just based off the actual question saying, hey, area of a circle, that probably means this function here creates some kind of circle, right? So let's see, could do a couple things. Could say, hey, let's plug in some values, right? And get out what the function could be. Or let's just go ahead and use a graphing utility. And look at that. And it makes a half a circle at least, right? Semicircle there. So I'm going to go back and try and draw that. And it does look like 3 is in the middle. All right, so we want just the area from 3 to 6. And because 3 is right in the middle, and this is already a half circle, so the area of a circle is pi r squared. But I have half a circle already, and then I want half of that half. So really what I want is a quarter. So pi r squared divided by 4. And then in this case, our radius is going to be 3. So pi times 3 squared over 4, which is just going to be 9 pi over 4. And then that is it for that. Didn't have to use any kind of integration rules just yet. But again, not every function is going to have a nice geometric shape that we know the area of, right? So sometimes we can use geometry, sometimes we can't. All right, so there's something else I want to talk about, is dealing with negative area, because so far we've been dealing with graphs that were above the x-axis, whether it's like this and we wanted this area, or we had, some kind of curve, and we were making rectangles to get this area here. But we have this idea of negative area, right? So negative area is if the graph goes below the x-axis. So let's say maybe we have something like this. Right, so this is positive area, and then anything below the x-axis is negative area. And what we do is, like if we're wanting the area from 0 to, let's say, 10, if I can write that here, 10, then we would add up all the areas, right? So we would add this, let's just say it was 5. So 5, and then let's say this also was 5. So that'd be a negative 5. And then this, that looks like half of what I already had there. So let's say 2.5. So then plus 2.5. And then adding all these areas is going to give us what's called the net area, right? So we'll keep that in mind as we move forward here. All right, so we may have pieced together the integral pieces before, but just as a little reminder here. All right, so we have this little, I call it a little S symbol here, because it looks like a funny shaped S, right? That's the actual integral symbol. A and B should be new to us, because before we didn't have, or at least we didn't define this A and B here. So A is going to be the lower limit, or the lower bound, and B is going to be that upper limit, or that upper bound. The f of x part, that is the integrand. And then the dx, that is the variable of integration, right? And for the most part, for us, it's going to be either x or it's going to be t. And we're only doing one variable in Calc 1, right? So let's go from a graph here. So use the graph to evaluate each of the following. Note that the graph of f of x consists entirely of line segments, a semicircle, from -8 to 13. So let's see if we can evaluate some of these. So we want the area under the curve from 0 to 7. So for 0 to 7, it's this trapezoid here, right? So remember, area of a trapezoid is 1/2 the height times base 1 and base 2. So the height in this case, because it's facing upwards, is 4. And then base 1 and base 2 are these things here. So here's base 1, or one of the bases. So from 2 to 5, that makes 3. And then the other base here is from 0 to 7, so 7 spots. So half of 4 is 2. 2 times 10 is 20. So that area is 20. And I'm gonna write it in a different color, just in case we need it later. Okay. Now let's go from 0 to 13. So from 0 to 13, we know that first part is 20. And then we now know what negative area is. So really, instead of plus, I should have put minus, because I'm going to subtract off this area here. It's another trapezoid. So 1/2 the height. This time the height is 3. And then the 2 bases. So 1, 2, 3, 4, 5, 6. And 1, 2, 3. All right. So let's see. We'll have 20 minus, and then was that 9? 9 and 3 makes 27. And that's 27 over 2. I'll go ahead and change that 20 to make that 40 over 2. And then 40 minus 27 is 13. So 13 over 2, or 6.5. So the area from 0 to 13 is 6.5. And I guess this trapezoid here, I could write in the area in case we need it. That's the 27 over 2. All right, from -6 to 0. So it's that semicircle here. So that's pi r squared divided by 2. And our radius looks like 1, 2, 3. So that's going to be 9 pi over 2, but it's below the axis, right? So it's a negative area. So negative 9 pi over 2. All right, we're looking from 3 to 3. There's actually no movement from a 3 to 3. Let me put the area here. Sorry, 9 pi over 2. There's no movement from 3 to 3, so actually the area is 0. All right, from 7 to 0, we've been going least to greatest, right? Or left to right. And in this case, we're going from 7 to 0. And when we go this backwards direction, the area is actually going to be negative. So we've done the area as 20, but because we're going backwards, it's actually a negative 20. And 10 to 4, so same idea here. We're going backwards. So it'd be the same as doing the negative area of 4 to 10 for the function. And let's see where that is. So from 4 to 10. Okay, so we have some smaller trapezoids to do. So that first chunk, we got 1/2. The height is 4. Base 1 is 1. Base 2 is 1, 2, 3. And then I want to subtract off the area of the other one. So 1/2 that height was 3, and then base 1 is 2, and the other one is 3. I don't have enough space here. Let's see, half of 4 is 2. 2 times 4 is 8. And then we have 5. 5 times 3 is 15, so it's 15 over 2. And then we'll change that 8 to 16 over 2. So I get 1/2. But remember, it's the negative of it. So it's actually going to be an area of negative 1/2 because we were going backwards, right? All right, from -8 to 13 is all of the areas added together because it's across the entire domain. So I need a first piece here, this triangle. All right, area of a triangle is base times height divided by 2, right? So the base is 2, the height is 4, and then divide that by 2. So that first part is 4. So if I add all those areas, I have 4 minus 9 pi over 2 plus 20 and minus that 27 over 2. So let's see. Let's get those all into common denominators. So that's going to be 8 over 2 minus 9 pi over 2 plus 40 over 2 minus 27 over 2. And I can combine some like terms. So I've got 8 plus 40 minus 27. It's going to be 21. It's going to be 21 minus 9 pi all over 2. And I could split that up, but I think I'm just going to leave it. All right? And I could, of course, get the decimal approximation, but I think I'm all right. Okay, so now we have two different scenarios here for these next two problems. So we want the derivative of f at -6. So let's go here. -6, the derivative at that point. And we have a weird scenario here. We're switching from line segment to semicircle. So because of that change in function type there, it's like a corner or a cusp type area. So actually there is no derivative. It's undefined because we have a cusp there. Okay. So let's see. Now we want the second derivative at 6. So here we are at 6, right? We do have a line segment, so I can find the derivative, right? Because derivative is just the slope of that segment. So we got 1, 2 over 1. So the slope is -2, right? So we have the first derivative at 6 is going to be -2. And since it's constant, right, the second derivative, the first derivative would look something like this, right? So the slope of that segment there is going to be 0, right? It's a constant. And what's the average rate of change of the function from 0 to 5? Remember, average rate of change is just another word for slope. So we want f of 5 minus f of 0 over 5 minus 0. So let's go to the function. F of 5 is 4. F of 0 is 0. 5 minus 0 is 5. So I get an average rate of change of 4/5. All right. So now let's look at some properties of integrals. I think we've kind of discovered a few already, but let's kind of formalize them. So, all right. So for the definition of a definite integral of f on the interval a to b, we normally have that a is less than b, right? Our integral usually has the lower number here, like 0 and then 4. So let's see, if there's some cases where it's the same. So from 0 to 0, which we saw a case up above. Or we saw some cases above as well if we had 10 to 4 instead of 4 to 10. So there's different properties that we've discovered that we're going to formalize now. So if the bounds are the same, there was no movement, and so there's no change, right? So our area would be 0. If we have those bounds that are backwards, it goes from greatest to least instead of least to greatest, then we just take the negative of the forward area, right? So we had already kind of discovered that above, right? Now, with integrals, we have this additive interval property. So if we're looking from A to B, and there's some C value in between, we could go from A to C and add in from C to B. So if I look at like this kind of interval here, let's see. We got A, B, and then we got some C value in between. So let's see, maybe we have something like triangular here. And then we have something like semicircle here. Not that it really matters. But this whole area from a to b of this function, right, would be the same as if I did one chunk first, a to c, and then c to b, right? And then here's some more properties. If we have a constant that's being multiplied, so like if I had 2x, I could really break that up into 2 and an integral of x. Sometimes it makes it easier. If I have just a constant, then what I have is I can pull the constant out, and then I just multiply by the difference of b and a. And this idea will show up here in a little bit. Okay. And then sum and difference. If we have functions that are added and subtracted, we can separate them. So if I had something like the integral from 0 to 4 of x squared plus 2x dx, I could split that up and say from 0 to 4 of x squared dx plus from 0 to 4 of 2x dx. And we usually will do it all in one step, but we're applying that property when we do that. All right. So let's see if we can apply some of these given values we already have, right? So we're going to use the properties to evaluate. So the integral from a to b for f of x dx is 8. The integral from a to b for g of x dx is -3. And the integral from a to b of h of x dx is 5/2. Okay, so let's apply something. So from b to a, that property is we're going to take the negative of a to b for the function. Well, we know that a to b for g is -3, but I want the negative of that. So actually, it's just 3. All right, from a to b of 2 times f of x, 2 is that multiplier, right? So the property we can apply is take the 2 out and then do the integral. Well, we know that a to b for f is 8. So total, this is going to be 16. All right, from a to b of 5, this is going to be 5, and then times that difference in the bounds. So 5 is b minus a. And then we have a sum here, so I can separate that and say, hey, integral from a to b of 5 dx plus integral from a to b of g of x dx, which we know g of x dx, that integral is -3. And then we just did this one in the problem right before, so it's 5 times b minus a. So to clean that up a little bit, we'll make that 5 times b minus a minus 3. All right, we have a difference here, f of x minus h of x. So I can split that and say a to b of f of x minus a to b of h of x. F is 8 and h is 5/2. So let's see if I combine these. We get 16/2 minus 5/2, which will give me 11/2. Okay, and then we have this next one. We have from a to 4 for h of x dx, and then adding in from 4 to b of h of x dx. So because these numbers are the same here, it's like having that c value. So really I can combine these and make that from a to b of h of x dx because those bounds right there are the same. So that gives me 5/2. Okay. Let's go a little further and talk about even and odd functions, because I think they have some properties that go with them, right? So, all right, we want from the integral from 0 to 3 of f of x dx is 8. What would be the value of -3 to 3? So we have some function, right, that from 0 to 3 is 8. So let's say if it's an even function, and this goes for any kind of drawing we're going to do here. Let's say the function is an absolute value. So on this side, here's 3, and this whole area is 8. Should do that in a different color. 8. Well, if it's an even function, that means there's symmetry, right? So it's the same on the other side. And we're going the same distance, right? It's -3. So that means this area here is also going to be 8 because of that symmetry. So if I talk about the area of both of those, I would be adding them. It's the same. So we'd have 8 plus 8, which is 16. Or really, it's the same, so I can multiply it by 2. So that area is 16. All right, odd functions are different. They still have symmetry, but a different kind of symmetry, right? So same idea, but I'm going to use an odd function. So an odd function could be like y equals x. So if I go from 0 to 3, still have that area of 8. And if I go the same distance this way, the -3, the area is still going to be the same, but this time it's not positive because we have a symmetry with respect to the origin. So we have 8 minus 8. That's going to give me 0, right? So that's a kind of cool little feature there. All right, we have something called the average value of the function. So let f of x be continuous over the interval a to b, right? So then the average value of that function on that interval is given by, we can find the area, right? That's that integral piece. And then we just want to find the average. So the average is multiplying by 1 over b minus a, right? So it says find the average value of f of x is x plus 1 over the interval 0 to 5. So we can do a couple things. So I'm going to try and draw it, see what we can do from there. We're going from 0 to 5. So 1, 2, 3, 4, 5. We're starting at 1, and then we have a slope of 1. So 1, 2, 3, 4, 5, 6. And we're just going up 1 over 1 each time, right? It's a linear function. And then what we have here, shape-wise, is a trapezoid, right? So 1/2 the height, which is 5, and then times the sum of the bases, which is 1, and what is that, 6? So 7 times 5 is 35, and then multiplying it by half, so 35 halves. So that's that area. So the area from 0 to 5 for this function is that 35 over 2. So now we just need the average value piece, which is that 1 over b minus a. So 1 over b minus a is 1 over 5 minus 0, which is 1/5. And then we multiply the two together. So 1 over b minus a from a to b for our function is 1/5 times the 35 over 2. And 35 over 5 is 7. So 7 over 2. That would be our average value. All right. And that is all for this section. So if you have any questions, let me know.